All right, so let's look at a totally different discrete distribution called binomial. So in this case, we are still not timed based, but we now only have two outcomes. The probability does not change between those two outcomes, so it's not a changing probability every time. And we're going to come up here to binomial. So this is based on something called the Bernoulli trials or Bernoulli experiments. And you have to keep in mind, each attempt is independent of the other. So there is replacement. So if you think about the bag of marbles, every time we're putting the marble back in and we're resetting it and starting over. And there are only two outcomes. So whatever of interest, it either happens or it doesn't happen. The probability of success doesn't change. It's not dependent on something else. It's not conditional. And the failure rate doesn't change either. And finally, you have a given number of attempts. So we're not going to just endlessly do this thing. We have a certain set of attempts. Here's some examples. If we flip a coin, that meets our requirements. So there's two choices. We either get heads or we don't get heads. And the probability doesn't change every time. It's independent every time. Rolling a dice, so we can either get a 6 or we can not get a 6. And the probability doesn't change every time. There's nothing conditional about it. Taking a stats quiz is probably not going to work with this distribution. There's too many other factors that would go into taking a stats quiz. So even looking at did I pass, did I not pass, probably not going to work. Different distribution. Winning a football game, no, there's way too many variables that go into winning a football game. That's one's not going to work. Drawing an ace, potentially, so we either draw an ace or we don't draw an ace, and assuming you have really good shuffling techniques every single time that you put it back. To do a binomial distribution, there is a couple of things that we need. We have to set a number of successes that we're hoping for, so something that we're looking for. We have a certain number of attempts, and then we have a probability of success. So we'll need to have all of those three. But before we do that, let's really look at an example. So Evans Electronics, they have a low retention rate for their employees. Management has actually seen a turnover of 10% annually, which is a lot. So they want to choose 3 hourly employees at random and estimate the probability that each person will not be at the company next year. So what are the chances that these people will be at the company next year? So here's how this is going to look. It's going to be a huge tree diagram. So we are going to start with the first worker. So we pick one person and we say, do they leave or do they stay? Those are their two choices. They have a 10% chance of leaving and they have a 10% chance of staying. And then we're going to add the decision of the second worker. And so it depends, it doesn't, sorry. So if this person leaves or stays, while these are independent activities, our probabilities change all the way over here because we are considering 3 different decisions that people are making. So this person leaves, and we now have the option of this person staying or this person going. If this person stays, we still have the option of the second person is either going to leave or not leave. Then we have the third worker. So again, regardless of these people's decisions, if this decision was made and this decision was made and this decision was made, we now have 2 more things that could happen. The third worker could leave or stay, could leave or stay, leave or stay, leave or stay. So these are independent of each other, but we are looking at the probability of all 3 of these happening. And then we come up with X. So this is the outcome option. So here we have 1, 2, 3 people left. So we're trying to see who's leaving. Over here we have 2 people that left. So leaves 1, 2, he stayed. Here we had 2 people leave, leave, stay, leave. So there was a 2. Here 1 person left and these guys both stayed. So right there. So 1 out of 3, we calculate their probabilities. Here's the formula of how to do that. And yes, it looks really nasty, but don't worry, here's the Excel formula to get it to do it for you. We can change this 0 to be 1 and make it a cumulative distribution. If it is 0, it is just a probability distribution. And then we can calculate the expected values as the others. So let's look at an example, and then we'll go to Excel. So what is the probability I will roll 3 values that are less than 5 on a 12-sided dice in 10 attempts? So I'm going to roll a 12-sided dice 10 times. What is the probability that I will roll 3 values of the 10 that are less than 5? So I know it's binomial because it has a fixed probability. The probability is not changing every time I roll the dice. I'm not accounting for anything else. And it has a fixed number of attempts. So in 10 tries, how is this going to work? What is the probability? So we can now figure out what is the probability of success. So let's go back to Excel. So less than 5 on a 12-sided dice. That means I can roll a 1, 2, 3, or 4. So there are 4 successes out of 12 options every single time. So my probability of a success is there are 4 options, 1, 2, 3, and 4, out of 12 total possibilities. So that is my probability of success for each trial. I'm going to have 10 attempts. And then I have my number of successes. So out of the 10, what is the probability that I will not roll any of these options? So I will roll a 5 or more every single time. If I had out of 10 options, out of 10 rolls of the dice, every single one of them was a 1, 2, 3, or 4, then that is the probability of all 10 being under 4. Luckily, we don't have to list all this out and do the whole huge tree diagram for this. Excel is going to do it for us. Using equals binom.dist. It is going to ask us for the number of successes, which is going to be right here. It's going to ask us for the number of trials, which we know is 10. It's going to ask us for the probability of success. And it is going to ask us for cumulative. Is it cumulative, true, or false? So that's that 0 and 1. So let's look at this. Equals binom.dist. It is asking me for the number of trials, the number of successes, comma, the number of trials, comma, the probability of success for each trial, comma, is it cumulative, true or false? So in this case, I'm going to say 0 because we are not doing cumulative distribution, we are just doing the mass function. Hit enter, I'm good to go. I can drag this down, or I can also double click this little corner and it will take it. Oh, no, it won't because I did not lock these. So if you do function F4, make these reference cells so it knows that it's pulling from those every single time, except for, no, that one we want to change. Now we can double click all the way down. There we go. So we're going to do the same thing here, except this time we're going to put a 1 for true and make it a cumulative distribution. So equals binomial distribution, successes, trials, and we're going to say 1. We're going to make these 2 reference cells, so either function F4, max, sometimes you can just put in the actual $signs. So we're just locking these 2 so it knows to reference these every time. We're not locking the A, so every time we go down, it is also going down. So once we do that, then I can double click. My cumulative probability should always end with 1 because it should be 100% at the end. All right, so over here, our expected value is going to be the probability times those, which we've done in the past. Double click that all the way down. Now I can take the sum of those and I get 3.33. So I'm expecting the chance of success to be 3.33 out of 10. We'll give you another hint. If we are just looking for the expected value, you can add those two together and it will be, multiply those two together. So the probability of each trial times your attempt, and you will get the same number. So that's how we're going to go about doing a binomial distribution.